Okay, I'm going to try to get through this in less than 10 minutes for you. But in this equation, they were asking you to determine the charge separation in hydrogen fluoride from the dipole moment. A lot of times in chemistry, they'll have a lot of words in there we don't use every day, and it gets confusing. But what I like to do is just pick out what it is that they're asking for and see what they're giving me and what's left after that. So in this case, like, it wants us to determine the charge separation. What do we know about charge separation? Probably absolutely nothing, right? Well, we do know that it's from the dipole moment. Well, what's a dipole moment? Here it tells you the dipole moment is equal to Q times R, where Q is the charge and R is the separation distance, right? So this little micro sign here is showing us that a dipole moment, because you see this is what a dipole moment is equal to this number with a big old D, and that's a Dubai. It's the way that dipole moments are measured are usually measured in Dubai. So what do we know? We know that Dubai is equal to Q times R. Well, what is Q? Q is measured in coulombs. This is the charge of an electron. And Dubai here is can also be converted to coulombs per meter. And then we have the R, which is separation distance, can be measured in picometers. Well, if you look at all of these units, if we're trying to whittle it down to one unit and we're using dimensional analysis, we're going to run into an issue where we're going to have more than one unit if we don't figure out a way to convert and cancel. So in the end, a dipole moment needs to be measured in Dubai. So as we do dimensional analysis, we're going to want to make sure that all our units cancel except for Dubai. Dr. Lindley was going over the hydrogen fluoride molecule and how we don't know if it's ionic. We don't know if it has a charge or what the charge separation is. Now, if this broke apart by electrostatic separation and it just boom, boom, floated off, it would have its own charge for H and F being a positive and a negative, right? And in this case, if it were 100% charge separation, it would look like this. Now, the thing is, at the end of the equation, we should be able to tell whether or not it would be 100% positive and 100% negative, or if it's less. So that's what we're determining. The charge separation here, if it looks just like this with no numbers here, it was 100% charge separation, okay? We're going to do dimensional analysis. It's a great way to make sure you keep your units canceling and everything lining up. So if you end up at the end of this with more than one unit and you're trying to get just Dubai, you'll know, oh, I did something wrong if you have more than just Dubai at the end. We know that the dipole moment is equal to Q times R. So we're going to take Q, the charge of the electron, 1.6022. I don't have my stylus. I'm sorry. I've never done it this way before. I have no idea where my bag went, and that is not normal. So we're multiplying Q times R, and R is here, 95 picometers. Now, I'm going to show you a chart of how to convert from picometers to meters. If you don't already have that memorized, there's the metric conversion chart is really good to memorize for these kind of things, which it's not as hard as it sounds. So this is going to be times 10 to the negative 12th to get it to go from picometers to meters, because when all is said and done, we need to be in Dubai's, and this equivalent here is in coulombs per meter. So we're going to have to cancel our meter. We can't cancel a meter with picometer, right? So we're converting this to meters so that we can cancel our unit. 1 Dubai, because we have to be able to have our answer in Dubai, is equal to 3.3356 times 10 to the negative 30 coulombs per meter. Ooh. Okay, so we can cancel our coulombs, right? And we can cancel our meters now. Left just with Dubai. So this right here was Q times R. And that's what we needed to get our dipole moment, right? But our dipole moment is not measured in coulombs by meter. Okay, that's why we had to do the dimensional analysis this way, where you end up canceling your coulombs per meter and getting the unit you want. So this was just a unit conversion after your initial equation. So when you type this into your calculator, you're going to want to do it with parentheses around these numbers, because your exponents will end up messing it up if you're not careful with your parentheses. Sorry, pickups again. When you do this in your calculator, you're going to get 4.56317. Our unit is Dubai. Ooh, cutting me off, are ya? Okay. Usually, you would take the lowest sig fig, significant figures, out of all of these. Like this one has 1, 2, 3, 4, 5. This has 1, 2, 3, 4, 5. This one has 2. That would mean we would probably use 4.6 as a number here, but Dr. Lindley used this whole number here. I'm just going to follow his lead. I don't know exactly why he did it that way, but he's the teacher, so I'm going to follow him. So we have 4.563 as our Dubais. Now, our next step is going to be to determine our charge separation. Right now we have our dipole moment. Okay, this is our dipole moment. Yay, dipole moment, we got it. But we have to do the charge separation from the dipole moment. In order to do that, you're going to have to take the part by the whole. You'll hear that. I'm going to erase all the ink here. 4.563 Dubais is your whole amount, right? That's your whole amount. What we want is the parts by the whole. The part would be what 1 is equal to. So we've got 1.86 Dubais as our part, and the 4.63 Dubais as our whole. And we're going to multiply that by 100 to get our percentage. So if we do the division on that, your Dubais will cancel, and you are left with 40.76. And in this case, there's 3 sig figs. You're going to round using this number, so you've got 40.8. Sorry, let me do a little. 40.8. Okay, so this is your charge separation. When you're labeling your charges, though, they're going to be labeled before they're multiplied by 100. Okay, so it would be 1.86 divided by 4.563, and that comes out to a plus for the hydrogen, right? It's always plus for hydrogen, and it's going to be a 0.407, but it's rounded. If you're going to do your 0.407 and you're rounding this much of it, it's going to be 0.41. And then this side is going to be a negative for fluoride, and then it's going to be a negative 0.41. And if you think about that, that is, according to Dr. Lindley also, it's a high charge separation. And then before we complete this, I will show you what I was talking about with the metric conversion chart. If you look at this chart here, picometers is 10 times, times 10 to the negative 12. So that's why we did that. And then, you could just use that. And this is the King Henry died unusually drinking chocolate milk thing that you can memorize. For those specific ones, I had some methods that made it easy for me to do the memorization from, I've memorized up to tera and then down to pico. I don't go below that. So anyway, I hope this helps.